Yeah, first of all, let me start by thanking the organizers for inviting me to this. It's my first time actually to this series conference. I so far enjoyed a lot because in Hong Kong it's kind of very isolated. It's wonderful to be able to join you guys here. Yeah, first of all, I would also want to thank Sebastian and maybe also Tess for finding this way forward for us. But we got the quantum molecule in 2015 and we spent like some years on loss measurement. We almost start to lose confidence about getting a condensate, but finally they found a way. Really wonderful work. And I started this for a long time already. I started working on cold molecules since 2002. Okay, when I become a PhD student. At that time, my PhD advisor, Bill Stwally, motivated me by saying, okay, you have BEC of items. If you can go to BEC of molecules, that's certainly wonderful. We already heard from yesterday's talk, there's really a trend to go to more and more complicated molecules, tetramer, trimer, and so on. Okay, I think that's many of the things are really happening. Okay, we are really turning impossible into reality. Although not in really fast pace, but indeed we're making advance. But of course, so far we are mainly working on the diatomic molecules, especially the polar molecule which has this dipole interaction. And with this, certainly there are lots of theoretical proposals which motivate us to pursue all of them. I want to say that many of these things are starting to become realized in lab in the last 10 years or so. Slowly, okay, it's still much slower than what has been done in the wonderful work in atoms, like you heard from Martin's talk yesterday. I would say this, it took us much longer because there are some roadblocks, of course. The first one is to molecules, of course, much more difficult to create, and also actually even detection can be a problem. Even more challenging is this, even for diatomic molecules, the interactions are too complicated to really understand exactly. So for the first problem in terms of creation, in the last 20 years or so, we developed two methods. One is atom association, starting from hard-cold atoms. We can go all the way to ground state. There's also this laser cooling, which for now we see more and more complicated molecules can be laser cooled and trapped. So we have basically two ways, okay, and to move us forward. But they have to admit, that's not perfect, and we're still facing challenges. For example, currently the molecular numbers are still relatively low, maybe 10 to the 5 are really large. So it'd be wonderful if we can somehow push this to, for example, 10 times more, or even more. So we are working with sodium-rubidium molecules. It's rather similar to the sodium-cesium. Just the dipole moment is slightly smaller, okay, and after basically after you set up a lab and you make the heteronuclear atom mixture and you find the perfect resonance. By the way, this is this step, I would say it's still a limit, especially for the person mixture. The atom to perfect molecule conversion efficiency is limited to about 10%. We heard from Martin's talk yesterday. There could be some fundamental limitation due to the free body physics near the perfect resonance. I also talked with Kai Dickman and so on. It seems like if you start from Fermi mixture, you make a bosonic molecule, you can have much higher conversion efficiency. They have something like 50%. Okay. So for us, actually so far we can make about 80,000 molecules. The density is 10 to 11. The temperature is 700 nanokelvin, which corresponds to a phase density of 1 part of 1,000. So we still need to do a lot of work to reach a BEC. So actually, one of the things we in early days we tried to test this idea for decay collision, try to test whether there's some difference between chemical reactive and chemical non-reactive cases. This here I want to emphasize, for many of the molecules. Okay, remember molecules have this vibrational degree of freedom, which so far has not been explored much. Maybe we should think about it, how to use this degree of freedom. For us, we try to use this vibrational excitation to control the chemical reactivity, because you find that the loss is exactly the same. Okay, there's really no difference. Okay, and with collaborative effort between many different groups and theoretical work, we basically now establish this picture, which involves when two molecules collide in the long range, they form this complex, and which then can be killed by the optical trapping light. So of course it's not 100% satisfactory status yet. There's still some question about for example the characteristics of the complex, especially the lifetime, how long that is, and how to understand it. So maybe so far, okay, like that, we already spent 70 years on loss. We don't want to study this anymore yet. But at some time we should go back here to give some clear answer about this issue. So of course, before we find the shielding method, we also try to use some brute force method. For example, use isolation by optical potential, including loading molecules into optical lattice. Okay, and quite a few groups do this, including us. And you can see here, after you shut off the collision, indeed, lifetime can be almost 10 seconds long. But one thing I want to mention is that the lifetime is really limited by photon scattering, because for molecules, since you don't have the cycling transition, so basically each photon scattering is going to cause one loss of molecule. So eventually, at some point, okay, the lifetime will be an issue. Also, so far, as far as I know, the lattice filling factor is not that high, so it's 30% or so for the best case for KRB and rubidium cesium in the fashion molecule. So this of course is another motivation for us to go to shield the collision and do the cooling and make a condensate and then do the lattice loading. So so that's my introduction, but everything else is going to be universal. So there is not too much to add, but Sebastian want to give a really nice talk and introduction. So really universal in the sense that techniques are also very similar. Okay, so now I'm basically going to the rest of the talk will be rather technical, in the sense I'm going to give you some of the details, which somehow Sebastian did everything right, but maybe he didn't have time to talk about it. But it took us some time to figure everything out. So of course, the idea of the shielding had been proposed for a long time, since everything happened in the long range. And you need to form the complex in the short range to get lost. So in order to prevent this from happening, you can certainly form a long range barrier, okay, and in a certain way. There are basically two ways. One way is to use the DC shielding, use the photo resonance. This has been so far demonstrated in KRB. I think that in Princeton, in ARB experiment, also have some results, but hasn't been published. Also, then the macro shielding, which is, I would say, more compatible with our kind of vacuum system, which is, once it becomes first demonstrated, becomes very popular. It has been done, for example, in NAK and also in ACS in Columbia. This is for the single macro shielding. We also did this. That's slightly later than Columbia. We just shine a single microwave, and immediately you see that you can really prolong the lab time by factor almost 10. Okay. And you can even understand some part of the loss. Okay, this is the loss versus the I think detuning of the detuning of the sigma plus microwave. You can see that at large detuning, the theory and experiment actually they agree quite well. Okay, but of course there's some problem in the small detuning. Okay. I would like to point out that all this the theoretical calculations were done by the group of Su Yi and Tao Shi in the Institute of Theoretical Physics in CAS, China. And we also tried with the cooling, because actually the elastic collision is really good. Actually, somehow, yeah, it's missing some. This is between Windows and the Mac probably. So this is elastic collision. You see actually the theory and the experiment they agree really well, because once again this is due to the universality of the this dipole-dipole interaction. And we also tried the cooling. You can see indeed, you can in certain range you can see the increase of the when we lower down the dipole trap, you can see the increase of the phase density, but similar to the NACS case for the single microwave dressing, stopped at a certain point due to the now understand due to three-body loss. So that basically promote us to find either better way to improve the loss, or but for us somehow we didn't take that way at the beginning. We tried to sorry. So yeah, I mentioned this three-body loss is also as we heard from both yesterday's talk and today's Sebastian talk, and due to this potential well, which is at even longer range before this barrier. I also want to point out that Tao Shi and Su Yi they worked out quite a few this effective potential, not only for single microwave but also for double microwave, which is very helpful for experimentalists. And they also, for NARV, they also did the calculation for the, for the field length states, but we haven't explored this part yet. So actually, after we finished the single microwave dressing, we spent some time to try to improve the atom to molecule conversion efficiency. For example, we even built this dual wavelength trap, try to make the sodium and rubidium cloud to overlap better. And we tried quite a bit about how to improve the conversion efficiency. At some point, we can get about 20%, but that involves a very small rubidium thermal cloud. Okay. So in the end, we don't get too much more, too many more molecules. So eventually, you found the recipe of making vast amount of molecules that use a really large trap to reduce the density of both atoms and molecules. So you also use a lot of atoms. Assume the conversion efficiency is more or less the same, and also do everything really fast. Okay, and then we were able to increase the number of molecules by about a factor of 2, okay, from 50,000 maybe to 80,000. Okay, but still the phase density is still 1 part in 1,000. And then when we were working on that, and Sebastian already put this this paper on archive, so we immediately dumped in. Okay, and so once again, it's universal. Okay, so everything is rather similar. Okay, because our antenna is a little bit different. We use a pair of top and down antenna to generate the sigma plus microwave, and use another loop from the side to generate the pi microwave. Like Jeremy already talked yesterday, for since our sodium-rubidium molecule has slightly smaller dipole moment So it turns out we need a higher Rabi frequency. Okay. So this actually have poses some challenge, because when Rabi frequency is higher, you need a lower microwave phase noise to maintain the dry state lab time. So one thing we did is we put a lot of filters in the microwave system, okay, including before the amplifier. You will even put a cavity, retinal cavity filter after the amplifier. With this, we can get the one-body lab time also on the order of 10 seconds. But a little bit unfortunately that since 4 months ago we had a lot of technical problems. We have not been able to fully optimize the microwave polarization. So the result I'm going to show you later on is going to be not that ideal. But so as you can see, once you have this double microwave, you can immediately see this additional improvement on the loss. Okay, this is almost another factor of 10, and we with double microwave shielding, you get compared with without microwave, so the factor of loss is improved. It's suppressed by almost a factor of 1,000. And then we also did a little bit on the dependence of the shielding on the. For example, we just keep the other 3 parameters and scan the tuning of the pi microwave. We found this nice curve, and in the lowest point, I have something about 3 times 10 - 13 centimeter meters cube per second. That's really low loss rate. But of course, this is since our microwave is not really optimized. Actually, you can see the shape. At this point, for these 3 parameters, the zero dipole interaction point is at about 16 microns. But in the experiment, because of the imperfection of the microwave, actually it shifted to this point. So actually, in the next, we want to say a few words about the detection. Okay, we already started to do the evaporative cooling since last August. Okay, so but then we because our experiment has already pretty old, so there are certain ways of doing everything, but really it took us a long time after we tried everything which didn't work, and then start to dump out of the box to think of other ways. One thing that's very important is the detection of the once you do have the cooling, how do you detect everything to get the real information. I want to remind you that in this kind of experiment, we use syrup to transfer molecules to ground state. For detection, we also need to do a reverse syrup, okay, to transfer ground state molecules typically back to fiber molecule and then do dissociation and detect atoms. Okay. One problem is that we have the Raman laser, which is on the horizontal direction. Okay, so for typical BEC experiment, we want to measure temperature and so on. You need time of flight. Okay, as you can see here, our Raman laser beam is only about 100 micron, and then you have, for example, tens of milliseconds time flight. The sample already dropped by some millimeter, definitely out of the Raman laser. This is one problem. Another problem is that we must have a time of flight expansion with ground sample. Okay, you cannot expand the fiber molecule because once you do the evaporative cooling, the density is pretty high. Fiber molecule has very large loss rate also. You don't want to do expansion for atoms either, because once you dissociate the molecule, the mass is different, so everything will be changed also. So you have to expand the ground state sample, which means that you must have the microwave on during the time of flight. Also, the dissociation, at the end of time of flight, you must dissociate everything really fast and do the image in very short amount of time. But then this also, have the third problem, which is, during dissociation, you could have heating. Okay. The image probe paths typically needs a tens of microseconds. That seems a very short amount of time, but depends on the amount of heating you have. Okay, it could actually cause a lot of problem. So we need to basically probe as short, as fast as possible, but you need to also optimize the signal-to ratio, because the molecules after the evaporation is already really low number, so your SNR is already very low. So you need to really consider everything very, very carefully. And everything must be done, near this paper resonance also. So for the first problem, for the for the falling problem, we just use some brute force method. We just put this galvo meter in there. We just at the beginning, the Raman beam is pointing to the trap position. We do the swap to make the quantum molecule. And during the experiment, we just tune the angle with the meter to to the corresponding time flight position, and then we do swap there for detection. It turns out it works quite nice, and we can have TOF up to about 20 milliseconds. The dissociation heating is typically a couple of different ways of doing the dissociation. Like I said, typically we go from quantum molecule back to pressure molecule and then dissociate. The first, we usually we use the magneto dissociation. We just ramp the B field in the reverse way to dissociate the molecules. But this is typically very long time. Okay, needs some millisecond time. Okay, and also depends on the ramping rate of the B field. You can have additional heating. And actually, several years ago, we developed a faster way of doing this that uses one photon dissociation. Okay, since this is the fast molecules really very weakly bound, you can just shine near resonant photon resonant to the atomic transition, then you can dissociate the molecules. But then, because of the excited state has pretty large line width, then you found actually this can heat up the sample really a lot. You can see here, even below threshold, there's some 200 microkelvin heating. At the beginning, we thought this is not a problem, okay, since we probe everything only in tens of microseconds. But it turns out once you want to work on BEC, this becomes a problem. So we then had to develop this, the two-photon dissociation method. We use a two-photon free-to-bound syrup. During the experiment, we tuned this pump laser frequency to just add the binding energy of certain molecule to it, and then we can drive from the quantum molecule to the free items. And this is actually this free-to-bound transition strength has a dependence on the magnetic field. Okay, it's closer to the resonance of actually the dissociation, the coupling efficient, the coupling strength. Okay, is actually larger. So we do this, like only 50 milligauss below the resonance. So we have to change the B field during the experiment also. So we have this efficiency at about 70%. So you can see that this is more or less speaking, this is during this probe. You can see one photon photo dissociation. You see in 100 microseconds, everything changed a lot. With two photon, just basically no change. So after all this effort, you can see that finally see some the signature. You see that with one photon, this seems like thermal gas still. That once again because with heating during the probe. But once you do everything right, you see this the real distribution. So with this, you can see then we can measure this rapid cooling. Because the microwave is not perfect, so actually our cooling efficiency is not as good as NACS. Okay, this is so there's still improvement we can do. And then we finally see this transition. This is when we keep decreasing the trap depth. We see this is from a thermal gas to a BEC. So far, we have about 500 molecules. To the best point, they have almost 17% of the molecules in the condensate. You can see that this distribution is tilted. We believe this is because of the misalignment between the two microwaves. Actually, our collaborator, we did the calculation. This is for 10-degree tilt between the two microwaves. You can see the interaction actually is also tilted along the same direction. So qualitatively, we understand this is due to the electrorestriction effect. So although our macro system is still not ideal, we tried a little bit, try to see how much we can tune the dipole-dipole interaction. By the way, we were not able to make a non-dipolar BEC yet. Okay, that's something we really want to work on after our system recovers. But even with the non-ideal system, we tried to see how much we can tune the dipole-dipole interaction. I think Sebastian also mentioned, with this 2 microwave, okay, you change some parameter, actually you can change the dipole-dipole interaction. For us, we decided to change the detuning of the pi microwave. So basically, since the dipole moment is determined by the rapid frequency and detuning, so you can have a smaller delta pi, then you have basically more oscillating dipole. When you have a larger delta pi, you have a smaller oscillating dipole, which means you have a residual rotating dipole-dipole interaction. And that's because the dipole length change. And then this is what we see. In the experiment, we first produced the BEC in this 16 megahertz. Afterwards, we just changed the detuning to different values. You can see here for detuning delta pi above this 60 megahertz, there's still gas phase, gas phase expansion. At larger detuning, that's when you have more rotating dipole-dipole interaction. We shall see that this cloud not expanding anymore. Okay, we think this is a droplet from NARB. And we have not been able to figure out the exact density yet because our image system, the sample is too small. Its vertical size is already limited by the resolution. Our detection system, the NA is only 0.2. So okay, with that I come to my conclusion. So this double microwave dressing really works very robustly. You can see that even though our microwave system is still not perfect, we can still observe like 1,000 times this loss suppression. We were able to do rather high efficiency of the cooling, although there's still room for improvement. And we already got this BEC of sodium-rubidium, and also we believe the first signature of NARB droplet. So currently our system is down. The Raman laser is dead. So once everything is recovered, we want to continue to optimize the micro polarizations. We believe that we can learn a lot from the Columbia group and also the MPQ group. We really want to be able to control everything nicely, so that to be able to tune the dipole moment, dipole interaction in more controlled manner. We also want to basically tune the dipole interaction to explore the different quantum phases. So with that, I would like to thank my students, Dajun Wang and Dajun Wang. They are the 2 guys mainly working on everything. Those are all 3 first-year students. I also would like to thank my theoretical collaborators and especially the guys in the ITP, Flin Deng, Su Yi, and Tao Shi, and also my long-time collaborator, Olivia and Gu Wan. Thank you very much.
Really nice questions.
Thanks so much. First of all, congratulations on the great results. That's really wonderful to see. And I had two questions. One is about droplet phase. You see in the pictures, you see that the signal kind of goes down as a function of time of flight.
Yeah.
And I was wondering, is that due to loss or is that due to imaging?
Due to loss.
Due to loss, I see.
Yeah. Mm.
And the second question was, you said the tilt of the microwave field is 10 degree. So what is tilted with respect to what?
It's a polarization of the pi microwave with respect to the propagation direction of the sigma microwave.
I see.
Mm.
Okay, I see. Okay, so
Yeah,
and I'm actually amazed that you see.
I believe that's the
Yeah.
that's the definition. Yeah.
Right, I see.
So yeah, this calculation. Okay, don't be misled by this. Okay, actually, we don't know exactly how much tilt we have. Okay, this is basically the best. Especially we don't know the azimuth angle. We only know the polar angle. Okay, we don't know which because our image has a certain orientation.
Right.
So it's a what we observe should be something between 0 and this.
Yes, yes. There's a lot of possible tilts in the
Yeah,
in the
yeah.
system. So for us, actually, if the pi would be tilted 10 degrees with respect to the plane of the sigma, I think we wouldn't see anything. We would see really breakdown of the shielding, basically.
Yeah,
But,
yeah.
I would guess might be a different type of tilt potentially. Yeah.
Other questions? I actually have one. This bound to free stirrup is very interesting. Any prospects of switching that around and using it to actually create your ground state molecule? Because I saw something like efficiency of 70%. This is kind of surprising.
Yeah, I think that in early days, there's a lot of study on how to associate it from atomic BEC to molecular BEC. Okay, I don't know the reason. Okay, it never really fully worked. Okay, for this process from the bound to free, I think it's more efficient because in the free state you always have more phase space. You have more place to go, so that can be more efficient. But the other way is less efficient. I think.